Coupling spatial and temporal coding, Part 2. We have seen that efficient coding scheme can give us directionally non-selective spatial-temporal filters in the retina. Such filters have a contrast sensitivity function G that spans the full range of spatial and temporal frequencies. In V1, things are different because different spatial frequencies, they are divided into different bands for multi-scale coding. Here I only list the magnitude of the frequency, so therefore this negative part is gone. And so let's say if we look at one band, let's say one particular frequency band, this will be this band with a minimum to a maximum spatial frequency range. And you notice that we also have a temporal frequency range, and that is imposed by this gain function. For any spatial frequency k, you have a minimum or maximum temporal frequency range that is much wider than the spatial frequency bandwidth. And as we can also see here, for instance, if we have spatial frequency 1 cycles per degree, you can see that it's most sensitive to 10 Hertz, but less sensitive to higher or lower temporal frequencies. So therefore, it's a unimodal sensitivity like we have here. And of course, for this spatial frequency range, we also have other regions. As for negative temporal frequency and another negative spatial frequency. Now, so let's integrate this spatial frequency decay not over the whole frequency range, but just limited within one band. And this will be the result. You can see that now the integration is only from a low to high spatial frequency range imposed by this band. And we have also combined a positive and negative frequency together, decay. So therefore, the exponential now becomes cosine. And we have learned that this kind of modification comes from the modifying of the unitary matrix into a multi-scale coding scheme. And that also includes this dependency on the output units M, which comes from if we impose the one-time complete rather than over-complete V1 coding. Next, let's also combine these positive and negative frequency omega, so therefore transforming this exponential also into cosine. So now we have omega from 0 to infinity, and this becomes cosine waves in time times a cosine wave in space. So this is the result. It turns out that there are also other additional freedoms in choosing the unitary matrix U in both space and time, and so that this is another valid filter for this spatial frequency band, and they are the same except that the cosines now become the sines. Neither of these two filters are tuned to motion direction. This is because each is roughly a space-time separable filter. This can be seen by if we treat this gain function as a product between a function of k and another function of omega, then this is roughly a product between a spatial function and a temporal function. So such functions are called space-time separable, although strictly speaking, this is also a function of k, so it's not exactly separable. But anyway, such functions are roughly space-time separable, so they are not tuned to any motion direction. And similarly, this function is also roughly space-time separable. However, these two filters have a quadrature phase relationship with each other because their spatial phase differ by 90 degrees and their temporal filters also, so that we can now combine them to make directionally selective filters. Here are two space-time separable filters. This is the result of adding them together. Here space is by the horizontal axis and time by the vertical axis. This curve shows the spatial filter in this first spatial temporal filter. It's an even function of space here. And this curve for the temporal filter, the temporal impulse response function, it has an initial excitation in the early time window and then a suppression in the later time window. This is the result of making a cross product of the spatial filter and the temporal filter. For example, you see this initial excitation to the central spatial region, and this becomes an inhibition at a later time. Here is the spatial filter for the second spatial temporal filter, and in this case, it's an odd function of space. Temporally, it has a temporal excitation in the early and later time windows and a suppression in the intermediate time window. Again, it's a spatial temporally separable filter. And now you can convince yourself that adding these two space-time separable filters together, you get this one. And it's no longer a cross product of space and time. Its current response is excited by a white spot at location x1 at time t1 ago, and by a white spot at location x2 at time t2 ago in the more recent past. So this filter is excited by a white spot moving from left to right, or by a black spot moving from left to right at a slightly spatial temporal offset location. So this is a space-time inseparable filter. It's excited by rightward motion but not leftward motion, and its motion direction selective. This filter integrates these two frequency regions for one direction of motion but not for the other direction. If you replace this summation by a subtraction of these two filters, then the filter will prefer the other motion direction and will integrate these two frequency regions. However, in general, neurons are typically not purely for one direction or the other, but rather it's a combination of the two motion directions with weights A+ and A- respectively. One can then characterize the directional selectivity of these neurons by this index. And this index will be 1 if the neuron is purely for one motion direction, this one or that one, and 0 if the neuron is not tuned to direction at all. For more mathematical details, see the textbook. In particular, these amplitudes, A+, A-, and the phases of the reciprocal fields and how they should differ between neighboring neurons in V1 are constrained if the V1 code is one-time complete. However, the degeneracy of the U matrix for multiplexing enables the freedom to choose these variables, parameters for the neurons. And therefore, because V1 is actually overcomplete, this means that there is a spectrum of direction selectivities among the V1 neurons. We recall that for each pair of frequencies, k versus omega, the speed of the spatial temporal Fourier wave is just the magnitude of this velocity v. So therefore, the speed is just omega over k. And we can just look at this quadrant in a frequency space if we only care about the speed rather than the velocity. So the speed is just the slope of this line. Therefore, for this spatial frequency band with this range of temporal frequencies, the smallest speed is represented roughly by this shallow slope line and the largest speed by this larger slope. And so you can see the larger speed is multiple times the smaller speed. And so therefore, neurons can be driven by a large range of speed, so they can at most be only weakly tuned for the motion speeds. If we look at a band of smaller frequencies near the zero frequency, then the temporal frequency range will include higher temporal frequencies. This again comes from the contrast sensitivity functions. We can also see it here. At a smaller spatial frequency, say at 0.3 cycles per degree, the contrast sensitivity is higher at a higher temporal frequency, 20 Hz. However, at this 3 cycles per degree, you can see the sensitivity is higher at a lower temporal frequency, 10 Hz. Yeah. Similarly, when we look at a band at a higher spatial frequency, say here, higher spatial frequency, then the temporal frequency range shifts to lower values. We can also see it here at higher spatial frequency range. The sensitivity to 20 Hz, higher temporal frequency, drops faster than those two lower temporal frequencies. This is expected from the gain control prescription for input signal powers that decrease with frequencies, so that it should give these kind of temporal sensitivity curves, for example, with sensitivity versus temporal frequency, and each curve is for a different spatial frequency. So, for example, if you take a spatial frequency of 0.5 cycle per degree, this is the blue curve. It's preferring higher temporal frequency. However, if you take a higher spatial frequency, 4 cycles per degree, okay, so maybe here, okay, and then it's preferring low temporal frequency, yeah, so high spatial frequency, low temporal frequency, low spatial frequency, high temporal frequency, expected from these kind of input signal powers. Then for these 4 different spatial frequency bands, for example, these are the types of the spatial temporal filters we could expect. Again, space is along horizontal axis and time is along vertical axis, as this is 0.5 cycles per degree, 1 cycle per degree, 2 and 4 cycles per degree, and so on. So as the preferred spatial frequency increases, the residual field sizes decrease, as we can expect. And meanwhile, temporally, this filter is sensitive to faster temporal changes than this one, and then this one. So as the residual field sizes become smaller, the optimal speed also decreases.